Hot chocolate versus heat loss, a cup showdown investigation. 3 sample cups were tested to find which could keep the hot chocolate warm the longest. A paper cup, a ceramic mug, and an insulated thermos. To start the experiment, 350 grams of hot chocolate were poured into each sample cup. The room temperature was measured at 70 degrees Fahrenheit. During the experiment, each cup of hot chocolate was stirred continuously, and temperature was measured every minute. It took the paper cup 9 minutes and 36 seconds to reach 140 degrees Fahrenheit. The ceramic mug took 8 minutes and 51 seconds, and the thermos took 13 minutes 58 seconds. To estimate how long the hot chocolate cooled from 160 to 140 degrees Fahrenheit, I treated it as a lumped system with a uniform temperature. I built the thermal resistance network, with the side losses in series and the top surface in parallel, which gave me the overall heat transfer coefficient, HA. Using that HA in the lumped capacitance equation, the predicted cooling time comes out to 11 minutes and 48 seconds. For the ceramic mug, I use the same uniform temperature assumption, but the heat loss path changes because of the thicker ceramic wall and its higher conductivity. After building that resistance network and solving for the overall HA, the cooling curve drops faster than it did for the paper cup. With those values in place, the predicted time to cool from 160 to 140 degrees Fahrenheit comes out to 9 minutes and 48 seconds. For the thermos, the heat loss path through the sidewall was far more insulated. The resistance chain ran through the inner metal wall, the convection gap, the vacuum region, the outer wall, and finally convection to the surrounding air. All of those were in series, and that entire sidewall path sat in parallel with the convection resistance at the top. When everything was summed, the sidewall resistance was enormous, essentially shutting down heat flow through the walls. Almost all the cooling happened through the top, which matched the experiment perfectly. The thermos walls stayed cold, unlike the ceramic mug where the lower side resistance let heat leak out and warm the surface. With that network, the predicted cooling time from 160 to 140 degrees Fahrenheit was 28 minutes and 48 seconds. For the paper cup, the measured cooling time was 9 minutes and 36 seconds, very close to the calculated 11 minutes and 48 seconds. The real cup cooled a bit faster, which makes sense. The model uses idealized resistances, so the actual heat loss ends up slightly higher than the prediction. For the ceramic mug, the measured cooling time was 8 minutes and 51 seconds, very close to the calculated 9 minutes and 48 seconds. The real mug cooled a bit faster, which, again, is expected because of idealized values in the calculation. For the thermos, the measured cooling time was 14 minutes and 28 seconds, compared to the calculated 28 minutes and 48 seconds. The larger gap here was expected. The thermos has a much more complex resistance network, and the model treats the vacuum layer as an almost perfect insulator. Even a small increase in the effective conductivity of that vacuum, making it slightly less ideal, causes the predicted cooling time to drop dramatically. So overall, if you're drinking hot chocolate from an open container, the thermos holds its heat the longest. But even then, the perfect temperature window doesn't last forever, so if you want it just right, you'll need to drink it quickly.